Momentum is one of the fundamental quantities in the universe that is conserved, uh, and along with conservation of energy, conservation of charge is another one. There are various. I think there are 7 quantities that are always conserved, as far as we know, and momentum is one of them. So we know our impulse momentum theorem says this, that F net times time equals m delta v. So if the net external force is 0, then momentum is conserved. So anytime there is no net force acting on a system, then the total momentum of the system is conserved. So any isolated system will have the same momentum before and after anything that happens. We're mostly going to be dealing with 2-object systems, but the principle does generalize to as many objects as you could want. Now let's go back. When we talked about Newton's third law, we talked about our 2 ice skaters. We had our 2 ice skaters that push off each other, and the forces acting on them are equal and opposite, and so they both get pushed back. Well, we can think about this situation in terms of conservation of momentum as well. If we consider these 2 people together to be our system, then there is no net external force acting on the system. They're exerting force on each other, but they're internal to the whole system, and so there is no net external force, which means that our total impulse is 0, and so then our change in momentum, we have 2 objects, and so the change in momentum of these 2 objects has to add up to 0, so that m1 delta v1 minus m1 delta v1 equals m2 delta v2. So the momenta of the 2 after they push are going to be equal and opposite because their initial velocities are both 0. Now, let's say, for example, the skater has a mass of 85 kilograms while the other has a mass of 65 kilograms. They push off each other. We want to compare their momenta and their velocities. Okay. Momentum is a Latin word, so that the plural is momenta, not momentums. So we want to compare their momenta and velocities. Well, if they both start from rest, so they're P01 equals P02 equals 0. So they both have initial momentum of 0, which means that the total momentum of the 2 afterward has to be 0, which means that their momenta are equal and opposite. Now, what about their velocities? Well, one has a mass of 85, one has a mass of 65, so we have, let's say that the person 1 is the 85, and both of their initial velocities were 0, so we just have their final velocities here. So we can see that the velocity of person 2 is going to be greater than, well, the magnitude of the velocity of person 2 is going to be greater than the magnitude of the velocity of person 1 because person 2 has less mass. And we could plug in numbers and get values, but the math there is easy. Just the principle is what I want you to get there. We're going to look at a couple of examples where momentum is conserved. Let's look at this problem. We have a skateboarder with mass 68 kilograms on his 0.98 kilogram skateboard, and they're at rest, and he jumps off moving forward with speed 0.1 meters per second. What is the velocity of the skateboard? When we ask a question like this, we're thinking of the velocity of the skateboard immediately after he jumps off. It won't take very long for friction and whatnot to decrease the skateboard's speed, but we're talking about immediately after he jumps off. And in this case, we can say the net external force acting on these two is 0. So 0 is equal to the momentum of the skateboarder, which is mv, plus the momentum of the skateboard, which is mv, velocity of the board. And some quick algebra gives us that the velocity of our skateboard is 68 times 0.1 divided by minus 0.98. We get the velocity of the skateboard is minus 6.9387, or about 6.94 meters per second in the opposite direction from where the skateboarder is moving. If we take a similar question here, though it may not look like it on the surface, we've got a cannon with mass 1,600 kilograms, and it fires a cannonball with mass 10 kilograms. Cannon recoils with a speed of 0.3 meters per second. What is the speed of the cannonball? I don't know if you've ever seen an old movie, but when a cannon fires, it's like, and it jerks backward. And that's because of conservation of momentum. So if we do the math on this, momentum is conserved, so the total momentum change is 0. They're both at rest to start off with, so they start off with 0 momentum. And we've got a cannon with mass 1,600 kilograms, winds up with a speed of 0.3 meters per second. And we've got a cannon with mass 10 kilograms, or the cannonball, and the velocity of the ball. So we can figure out the speed of the ball there, and figure out that the velocity, the speed of the cannonball is going to be 48 meters per second. I've kind of been framing this in terms of the impulse momentum theorem, but really, what we have is that 0 equals a change in momentum, right? And a change in momentum is a momentum final minus momentum initial. So another way of writing this, or another way of thinking about this is that initial momentum equals final momentum. And then depending on how, you could have an arbitrary number of objects, so this initial momentum is going to be m1 v1 naught plus m2 v2 naught plus, however many objects there are. And the final is going to be m1 v1 final plus m2 v2 final, etc. And we're going to look a little bit more at this in the next video. For now, one more example that I want to consider. Let's say we've got a bomb, and this bomb explodes. So we've got a bomb, fuse, okay, and then the bomb explodes, and there's little pieces going off in all different directions. Initially here, the bomb has 0 momentum. There is no net external force acting on the bomb. So after the explosion, our final momentum must also be 0, which seems kind of strange, but our final momentum is 0. Like, all these different pieces going off in different directions, their total momentum is going to cancel out. So even though there's, here there is 0 kinetic energy, and over here there's lots of kinetic energy. So there was, energy stored in whatever was the explosive was inside the bomb. So then that energy is released to kinetic energy over here, but momentum is still conserved. So momentum is conserved. Kinetic energy not necessarily conserved.